we continue with Yair Glasner on Boomerang subgroups.
Hi, thank you. So as I promised, I'll change here today. I talk about kind of different nature of results. Everything I'm talking today is joined with Tobias Hartnick and Waltraud Lederle. And today we focus on the, so far we were kind of talking about a situation where there are no kind of rigid type situation where there are few IRSs, and we kind of generalized it, showing that there are a few boomerangs, and now we want to talk, just to somehow to show that this is an interesting concept, to show that these actually do show up. And for this we focus today solely on one group, F2, generated freely by, say, A and B. And if you want a comparison, you can think of it as a lattice in SL2R. So it kind of contrasts what happens at the higher rank case. So maybe before saying what we do know, let me start with an open question that we were trying to answer and we do not know how to answer so far. So open question: is there a boomerang delta in F2 or for in any other group for that matter? I don't. In a way, this is kind of universal, if you like, and I'll explain why in a minute. Such that the orbit closure of eta of delta does not support an IRS. This would really kind of be this would really kind of provide a very good example for a boomerang that really does not come from an IRS. There are very easy constructions giving almost this in a very cheap price, and this also explains why I said that F2 is universal. So here is an almost example. Take say G to be any group without an I. Let G be a torsion group with no IRSs. So it's not so easy somehow to construct groups without IRSs, but there are many examples. So one example, for example, is the Tarski monster, which to begin with has only countably many groups, or countably many subgroups. So once you have a countable set, any measure, any invariant measure that's supported on it is actually supported on a finite orbit, and therefore any IRS here has to be either delta E or delta of the whole space. But there are other groups. So example, you can take SLN of the algebraic closure of FP. In fact, it's shown that for and in some ways we can also just show it from our work. I mean, the same proof that I did yesterday will show that these groups do not really admit IRSs if you take a countable field. There are no longer finite index candidates, and again, these two are always there, and that's somehow the problem. Now, F2 is universal in this sense. I mean, you know that from your first course on group theory that you teach or anything, that if you have a short exact sequence, then there is a correspondence principle between subgroups of G and subgroups of F2 that contain the kernel, right? There's a one-to-one correspondence between subgroups of G and subgroups of F2 that contain the normal subgroup. And if you think about it, it's a nice exercise to see that this is actually not just abstract correspondence, but it also agrees with the topology and the group action in the sense that this is really a homeomorphism of topological spaces. Moreover, G of course acts here, F2 acts here, but it acts with this normal subgroup acting trivially, so it factors through an action of the quotient, and therefore you really get an isomorphism of dynamical systems. So this whole kind of basic group theoretic information comes up to the topological level, and in this case you can take such examples and translate them back into here and get also inside F2 invariant subsets, closed invariant subsets. Sometimes they're not only closed but even open, if you take this Tarski monster example, that hardly support any IRSs. They support just two IRSs, namely delta n and delta of F2 itself. But that already kills it, and we don't have any actual good example because these are always there. So actual examples with no IRSs at all have to be supported not on subgroups somehow. I mean, not on something coming from a group. So here's a. I mean, I'm going to try to talk about construction of Boomerang subgroups. But let's do like a baby version beforehand. So because the proof itself is a bit technical, so baby version, which I think is a very good exercise to do. It has to do with the question of how do you construct subgroups of F2 or of any group altogether, and for this you bring up something else from your first group theory course, namely that there is a one-to-one correspondence between subgroups of F2 and actions of F2, at least transitive actions on a set. Just by the orbit stabilizer map, at least if I take a pointed set, so for every subgroup here I associate the action on the coset, and vice versa. If I have an action here, I can take the stabilizer Now, of course, subgroups correspond to transitive actions, which is what prevents me from giving a name to this set, because it might be either finite or infinite. But let's forget about this and just call this set Z. And now, really finding subgroups inside a group gives rise to, study or understanding the permutation representation theory of that group, which I think philosophically at least, this is a good indication of why the subgroup structure in group theory is always a delicate business somehow, like a difficult question. Because, somehow math theories fall into, different categories, and representation theory into locally compact setting always admits, or not always, but typically admits interesting structure, and into a Polish target, representation theory gets much more wild, and the symmetric group of Z, it admits a nice infinite Polish structure, but it's definitely not a locally compact group. So in many ways, it's like the simplest example of a non-locally compact group. So we want to construct here subgroups by taking representations, by tackling the representation theory. And the question I want to arise is, what happens with the generic type of representation? If you just randomly pick a subgroup in this sense, that you pick a representation from F2 into this infinite symmetric group. So one of the first papers I wrote in my postdoc I did with Nicolas Monod, and he likes to call this group like this. So here's the guideline question: what does a typical row from F2 to this symmetric group look like? And you can say, well, it's not a locally compact group, so there's no measure here, and you can't really ask about typicality, but of course we can appeal to the bare theoretic point of view. And the first thing that you notice is that right, this by definition it's a Polish group, it's a bare space. And the first thing that you notice is that you get something utterly uninteresting. Like it's an exercise in bare category that if you look at home F2 into this group, which is just admits a Polish structure like this, because you just send the two generators, then almost surely all orbits are fine. No, almost surely, I mean, I won't use the word almost surely. Let me say generically, almost all orbits are finite. In fact, it's an interesting thing. It does turn out to be an interesting situation in the following sense, that sometimes when you do infinite random or generic situations, you have this pool of possibilities. You push your hand inside and you look at what kind of permutation representation you got, and whenever you do it, you pull out the same thing. So not only this is all orbits are finite, but there is one specific permutation representation that is kind of generic in the sense that this is the only one. It's like a dense, it's a residual conjugacy class inside this whole space.
Let me ask, so what orbits are you thinking about? Because now you have a pair of permutations, right? So what orbits are you thinking about?
Sorry, I have what?
What orbits are you thinking about? You have an element of...
Yeah, I take A and B, and I look at a generic pair of infinite permutations. I choose them. I'm looking at this space, okay?
Right.
So I get a permutation representation of F2.
Okay.
And I'm saying that there is a specific permutation representation that is generic in this sense, okay? And this kind of, if any of you were here yesterday, not yesterday, last week, it kind of mimics the Nikanor's talk, who described also a similar situation, and somehow in the group theoretic setting we have a similar statement to his, namely, what are the types of groups such that if you take a generic permutation representation, there is one generic one that always comes up, and it turns out that this is equivalent to the so here is a theorem. It's mine joined with Kitroser and Melleray. So gamma has a generic permutation representation if and only if the isolated subgroups are dense in sub-gamma. A slightly weaker condition would be that the finite index subgroups are dense in sub-gamma, and this is exactly what is called in group theory the Lerf property. So kind of every Lerf group, and in particular surface groups, hyperbolic three-manifold groups, and Gregorchuk's group, and so on, all of these have their property. But also groups with, for example, countably many subgroups, like the nilpotent finitely generated, or like the Tarski monster, they also fall into this pool. But from our point of view, was just, I was kind of got sidetracked, but from our point of view, this situation is not interesting because all it gives in this situation is finite index subgroups, which are exactly the isolated subgroups in the Chaboty space of the free group. But this is often the case where you play a bare category game. I mean, when you look at your first approximation, you get that almost everything in your box is just uninteresting somehow, if you're looking for interesting objects. And this is a situation that comes again and again when people do bare category, and then you somehow, if you manage to restrict and give a new Polish structure to what remains, then you start finding interesting things. Okay, so there are various ways to kind of ignore this big bad part and get acquainted with this part that is left here. And in the paper that I'm going to discuss today, we do the easiest possible solution because the problem was hard. How do you force a representation of F2 not to have only finite orbits? Well, let's take A and just say, okay, we don't pick that randomly. We pick A already, so it guarantees an infinite order. And in fact, so definition, a restricted permutation representation rho, let's say, let me write just the restriction of all, the collection of all restricted permutation representations is just all the phi from F2 to the permutation group such that AN is n plus 1, just mapping A to the shift. So I'm forcing it to be really not just infinite orbit, but actually the best thing that you can take, the infinite permutation. And of course, then this is equivalent as a Polish space to the group itself, because the only question that remains is, where do you send B? And so here we are safely inside the green region, and an exercise that, is kind of folklore, but we wrote it into the paper anyhow because I didn't know where it's written, but is that here you start getting interesting actions, and in particular interesting subgroups. So generically, bare generically, the phi of zero, phi F2, the stabilizer of 0, so the group corresponding to a generic, for a generic restricted phi has the following properties. You know what, let me not talk about the subgroup, but actually about the permutation representation. So we can talk about the permutation representation. Well, it is, it has a dense image. It acts amenably on Z, and it has a faithful action. Kind of three very nice properties that you are interested in. A dense image is what is known in permutation group theory as being highly transitive, namely it's kind of k-transitive on k tuples of distinct points, but for each, for every possible k. So it's like 2 transitive, 3 transitive, so you start getting interesting things. And in terms of the stabilizer, if you want to do this dictionary, you can translate it to properties of the group just by adding the small letter co. Right? This is a co-highly transitive group, a co-amenable group, and it is core-free. Co-highly transitive groups, in particular, are maximal subgroups. So
what is sub-zeros?
Sorry?
Stabilizer of a point. Stabilizer
Okay.
of 0.
Okay, thanks. No, the right-hand side is stabilizer of a point.
Yeah, this is a stabilizer of 0. This is in this correspondence between
Yeah, sure.
Where did I write it? Subgroups and permutation representations. This is just this type of equivalence. So let's do for a minute this high transitivity just as an example of how this works. Instead of an action, it's usually convenient to think of a Schreier graph. And the Schreier graph looks very nice here because A just acts like a line, and and then it is B that acts randomly. And in order to say I want to do three transitivity, okay? So I somehow want to convince you that I can take these 3 points and do some prescribed thing for them. Maybe take this to itself, this here, and that one, I don't know, here. Okay? And, whatever I told you, I can make life even more difficult for myself, and let's put in more restrictions just to make it, some well-defined finite permutation on some, maybe very long, but some interval. So, what is since I'm doing bare category, I'm allowed to intersect, countably many things. So it would be enough if I show that for, the condition of the group admitting such a permutation is open and dense in the collection of all possible choices. And you say, okay, but what is why would B do something like that? I don't want B to do it. I want some word in A and B to actually achieve this permutation. So B is something else. I don't know, maybe it sends this here and this here, okay? But I could keep drawing this infinite line. And what is the chance that somewhere along the line I will see exactly this green picture drawn in red? Right? Of course, this is an open and dense condition, so I will see this somewhere here, whatever I wanted, right? And then I can conjugate it back using A. I can use not just any word inside the free group, but I can do A to the K, B, A to the minus K, which basically translates whatever picture I see here back to the identity where K is exactly, the first place that I found this situation. So this kind of proves the high transitivity clause. So how do you pull this to generate not just individual subgroups, but IRSs and...
So can I ask, so here, for example, the definition of highly transitive, it really means that the action on the coset space is highly transitive, or is it? Okay.
Yeah. Coamenable means amenable.
Coamenable means coamenable, not amenable. It means that action on the coset space is amenable in the Greenleaf sense of the word, in the sense that you can see Fellner sets, right? Yes. And this is, of course, true, right? That's the easy part somehow, because A definitely acts amenable here. It's just the action on itself. And B has finite orbits. Just take as many of them as you like consecutively, and you will get a Fellner set. So this is completely kind of dual to being an amenable group. The free group doesn't have very many amenable groups, but for a normal subgroup in general, being Co-amenable means that the quotient is amenable, not that the group is amenable. And here it's not a normal subgroup, so it's a more general. So it was kind of Louis Bowen's idea to generalize this kind of I don't know, kind of imitate this in order to generate IRSs. At the time, he was interested in doing IRSs. And the first few things, so you know, IRSs are just not actions on sets, but actions on probability spaces. And the first things that you try just don't work. I mean, if you look instead of homomorphisms into the full symmetric group, into this Polish group, then you'd get only 3 actions, no matter how you do it. So maybe the next best thing, and this was Lewis's second idea, is you look in the homomorphism into the Polish group of all of the full group of some equivalence relation. Should I'll explain a bit later, okay? But I think everyone knows this, right? And the same bad thing somehow happens, almost generic. So generically, your action is free here. You don't get any IRS, and here generically the action is periodic. Namely, you get only finite, you do get IRSs, but only finite index. Periodic in the sense that almost all orbits of the image group that you get here are finite. So now we get to the third thing. I mean, Lewis does something much more sophisticated. You know, instead of restricting to some very special model, he's trying to restrict and say something more conceptual on what is left after you missed this boring case. But we want to make life easy for ourselves so that we can prove nice things. So let's look at let us choose very carefully the equivalence relation that we want. Namely, I want one very nice generating element that is that I can just send A there in order to guarantee that the action is interesting. So here let R be a hyperfinite equivalence relation, Borel ergodic countable equivalence relation. And consider the restricted homomorphism from F2 into the measurable full group of this equivalence relation, and if you take this up and you insist that it's a probability measure preserving equivalence relation, then Bowen did many interesting things about that, and later Ami Eisenman and myself, we pushed it further, and we constructed IRSs satisfying all these nice group properties, namely IRSs in the free group that are supported on co-amenable, co-highly transitive, and core-free subgroups. So the whole point of this current work with Tobias and Waltraud is to remove the probability preserving assumption and hope that we can get interesting boomerang subgroups or interesting element-wise conservative actions that do not come from boomerangs, and this is indeed what we get. So let me just remind now, after saying this short thing, let me remind a bit about non-singular equivalence relations. But let me start with the actions. Okay, so instead of developing the orbit equivalence in general, which is not really relevant to my talk, I just assume that it comes from a V action. So it's a well-known theorem of Dye that every two ergodic probability measure preserving actions of Z are periodic are orbit equivalents. Let me abbreviate it like this, in the sense that, well, if gamma acts on X mu, gamma here is Z, and it acts also on Y nu, there is some measurable isomorphism between the two that does not intertwine the action, but it takes orbits to orbits almost surely. Okay, so phi of Zx is Z of phi x mu almost surely, and this is an isomorphism, automatically probability preserving. And there are two things here we want to get rid of: this aperiodicity and probability preserving assumption. And this was carried out by Krieger, and he noticed that when you leave these, then you do get many interesting examples, but still classifiable. So Krieger every ergodic V action falls into one of the following Krieger classes. One n, one infinity, 2, 1, 2 infinity, and 3, and there's kind of additional parameter here, lambda. All of you know it probably better than I do, but let's say it anyhow. These are just finite endpoint sets. This is the situation that we already did. This is the probability preserving case. Here I preserve an infinite measure. And this is where there is no invariant measure. I should have said non-singular, of course. because this is the case that interests us, right? And then to any one of these, you can associate the full group. So in any one of these cases, define the full group, the measurable full group, so this R, all the maps from X to X, kind of Borel bijections, such that X is, phi of X is equal to 2 to t to the n phi of X for some n depending on phi and almost all X. And this is this is a very nice group. It's a very large group. It doesn't admit a locally compact metric, but if you normalize your measure class to be of measure 1, it admits a very nice metric that makes it into a Polish space, namely the distance between phi and psi. This is kind of the uniform metric. It's a very strong metric. Is just the measure of the set of points X such that phi of X is different than psi of X. And with this in place, basically, by the way, for the specific case of lambda equals 0, there is an additional kind of subdivision of the orbit equivalence classification. But in any case, this is the setting that we want to do. I fix somehow this T, this generating automorphism, and our theorem says that for a generic, you know what? Let me assume. Let me kind of do away with these conditions. I mean, I just in a way I already did this. So let me assume it's aperiodic. Assume T as above is aperiodic, phi in F2 into the full group, but the restricted type of homomorphism that actually is bound to send A to the generator itself, and kind of just generically up to a meager set sends B anywhere, satisfies the following properties. One, almost every orbit satisfies these three conditions. Almost every orbit, the action is highly transitive, amenable, and faithful. the action, and this is the interesting part for us, is element-wise conservative. This is the part that was trivial in the 2-1 case. In the 2-1 case, you are probability measure preserving, so it just follows from Poincaré recurrence. On the other hand, when I'm not in the 2-1 case, then this is the difficult part of the proof, and on the other hand, I'm guaranteed that I don't have an invariant probability measure on that in the same measure class, because A itself is not of type 2-1. So there is no invariant probability measure even under the first generator. Okay. And if in addition the action is is not of type 2, is not measure preserving, namely it's not a probability, namely it's not, then 3, the image of phi is, namely phi, the image of phi is the whole group, so it gives a dense situation. This is true also in the 2-1 case, but it's not, we don't prove it actually, and it was proved a few years ago independently by Lemaitre. So, good, so I mean, I was kind of debating whether to try to tell this whole story because, I feel that most of you know these things better than I do, but I decided anyhow to do it, and I think it's just a nice story. Let's take a short break, and then after the break, what I will do is try to sketch the proof of 2, which is the most interesting part from our point of view, and I mean it's a bit of a technical proof, but I'll try to sketch it by pictures rather than by writing things on the board, which I think should be more engaging. Maybe just say that the outcome of this theorem, is that also in sub F2 there are admits uncountably many measures, non-singular measures, supported on Boomerang subgroups. So and these measures are not, most of them are, or many of them are not probability preserving measures. So they're not equivalent even to a probability measure. So it's some version of what we were looking for, even though the question about whether there is a actual closed orbit that doesn't support any IRS is still open, and we're actually thinking about it. So good. Let's do a short break. I think this is the best. Good, so before I actually start with the theorem, I want to advertise another thing. I think a really very beautiful paper of Waltraud, my co-author, Lederle, which attacks the exact same question but from a completely different perspective. So, namely, if you consider the action of F2 on its Cayley tree, she constructs, so she treats it from the point of view of the critical exponent of the subgroup. I mean, she constructs, so there are Boomerang subgroups delta in sub F2 with the critical, so critical exponent, let me not define, but it kind of measures the exponential growth rate of the subgroup of its orbit here inside the, so with the critical exponent, arbitrarily close to any given subgroup. So in particular, I mean, it's just a way of saying that the collection of critical exponents of Boomerang subgroups is dense. And you know, in the relevant interval, you know, between 0 and the critical exponent.
The critical exponent is a number.
Yeah.
Yes.
So arbitrarily close to any given subgroup.
To that of any other.
To that.
That, yes, sorry. To that. Sure.
Same objects coming.
Yeah, of course. So, and this stands with, you know, in contrast with the theorem of Levitt and Gertman, also recent, that shows that kind of like normal subgroups, critical exponents of IRSs are bounded. They are at most half the maximal. Sorry. Like the lower bounded by half the critical exponent of the big group, and in fact they actually have to be equal to the critical exponent of the big group if they are of divergence type. So this stands in complete contrast. This stands in contrast to Levitt-Gertman, saying that the critical exponent of delta is bigger or equal than the critical exponent of F2 half, or mu almost surely, for any IRS. And in fact, it could even be equal here. I mean, if somehow the IRS happens to be supported on groups of divergence type. So this is kind of another approach to showing that, you know, there are boomerangs that are really kind of very different from. But let me. So in the time that is left, I want to prove that, to try to sketch the proof of the element-wise conservativity clause in our main theorem. this is just a sketch, so I'm saying things that are, some of them are easy, some of them are tiresome to check. But the first thing that we notice just by, this is often the case, by the way, in bare type proofs, that the G delta property is easy to check. I mean, the difficult part is to establish, so G delta property is straightforward, is easy. Now, so I'll just focus on the density. And that's somehow very essential in this specific proof. It's possible to break the element-wise conservative actions as the intersection over all words in A and B to the condition that rho of W itself of A and B acts conservatively on X. Just let's look at the setting now. I'm fixing omega. It's some word in the free group, and I'm saying that for a generic choice of phi, assume that I can prove that for a generic choice of phi, this specific element in the representation will act in an element-wise, act as a conservative transformation on the space on which I'm acting. This condition is also G delta. And if this is a G delta dense condition, bare category allows me to conclude that this is also a dense G delta. So hence from now on, can fix once and for all some word in the free group. And we'll see somehow that it really depends on the maybe a nice an insightful remark is that it really depends on the behavior does depend on the word. Unlike what we like, the behavior does depend on omega. For example, if omega is some conjugate of, if omega is some conjugate of A itself, then it will be a conjugate of A. I mean, it will act just like A. And A is constrained to act as the generator of my equivalence relation. Okay, then it's ergodic and it's, of course, conservative by virtue of the understanding that ergodic transformations are conservative, okay? So this is one example. One other example is what happens if this is a conjugate of B. Well, B is just a bare generic element in the full group of the equivalence relation, and I told you, like, our first obstruction was that if you just randomly choose an element without any constraints, you will get something periodic, not very interesting. But still it is conservative. This is, so this is conservative by virtue of ergodicity, and this is by periodicity. But you see that it does actually depend on the word that we're choosing. So That's part of what makes this question a bit delicate. Kind of an essential definition is, okay, maybe before giving the definition, let me give kind of, so what we need is given some B0 epsilon bigger than 0. I mean, let me call it phi B0. So this is the map that sends A as required to T and sends B to some B0. Or maybe call it F, I don't know, just to distinguish between. Given some homomorphism, I want to prove density, right? So I'm given some completely general constraint homomorphism, and epsilon bigger than 0. What we want to find is and my fixed W, of course, for a fixed omega in the group, what we need is some H in the full group of the equivalence relation, such that the distance between H and F is at most epsilon. This is, I remind you, this is just the measure of the points where these two differ. It's a very strong topology somehow, right? In order to be close, two elements have to agree on almost all of the space, not just be close somehow, which is the more natural topology that makes the whole non-singular, or even that maybe not, but never mind. Okay, so this is the topology, and such that the given word of T and H is conservative. Okay, so this is our goal somehow. Now, the next step, or maybe a definition, I say that some element G in R has a range bounded by M if G to the K X is equal, you remember, I mean the full group. So this being the image of X, it has also to be the image of T, or some power of T. Right? This is the meaning of the full group. I'm acting with the same orbits that T does. So this is equal to T to the nx for every K, and with n less than m for every K. It's kind of stronger than what I just said about B already typically admitting finite orbits. So if I draw the same picture again that I drew in the permutation setting, then, but now this picture is measurable, so this is not actually an action on the set, but it's kind of a typical situation. It's a part of a big measurable collection of orbits. I know that for a dense choice of G, the orbit is finite, but what I would like to claim is also that I can kind of, in a very strong way, bound the range of these orbits to be bounded by using only finitely many bounded number of copies of powers of T. So here is an element of range 4. It acts like this. I mean, it could. It's not just about orbits of size at most 4, but also orbits that don't go far away. I mean, an orbit of size 4 could go whoever knows where. So this is the kind of an essential notion, and the easy claim is that for every epsilon bigger than 0, let me just say claim elements of finite range are dense. So here I should say also for almost every x, of course. Elements of finite range are dense, and therefore up to changing. Therefore, I can find some what did I start? Fg, some g in R, such that the distance between G and F is at most epsilon over 3, and the range of F of G is at most M for some fixed M. I don't care, maybe M is large, but I want to fix it once and for all. Okay, and the proof of the claim is just the following. I mean, I can write X is as a union of xi, where xi is the point in X such that G X is equal to T to the J of X for some J less than I. And of course, right, every point, this is an ascending union. Every point, almost every point admits such almost every. Okay, I mean, it's kind of a measure theoretic argument. Let's not get stuck on it. So I've kind of already changed so without loss of generality, I can assume, by changing B just a bit, that it maps to an element of some finite range. But now so the picture is like this, okay? You see, B has these orbits that don't go very, very far away. They can intermingle with each other, right? I mean, it's not like they are completely separated, but they can intermingle with each other. And almost surely all of the orbits look like this. But I want more. I want what we call a kind of a zebra structure on the orbits. Namely, I'm kind of dividing the orbits, so a zebra structure. Or a zebra stripe structure. On permutation representation is of the form, let me not write it but draw it. Okay, so imagine it's like this. And of course there are, the zebra has black and white stripes. Imagine the white stripes being much larger than the black ones. But what I really want is that, okay, here I have this nice bounded range structure. But within the black stripes, I just want the element B not to do anything. Just fix the black stripes. Fix the black stripes point-wise. Okay. So here is how we get it, and I'm trying to draw it as a picture. Okay. Before I draw it, let me just remind you what is the first return map. To get a zebra structure, we will use the first return map. So here the first return map assumes that I have a certain set. And the first return map is basically defined like this. As long as you're in your set, draw it bigger. Here is my set Q, I don't know. I have some element G, and as long as I'm in my set, I just act as G does, okay? Once I'm planned to go outside, I don't want it. I want to remain inside this set. So I just continue with my orbit as I'm possible, and then the first time I get in fact I continue this map like this. Okay, this is defined. It's a measurable substitution. you can define the first return map in a natural way. So this is the kind of thing that we will want to use. So let us fix some m much bigger than little m, which was the range that I fixed for my little element g. Okay, and I defer the decision of exactly how big this has to be for a later thing. And the picture I want to do now is, let's pick a very small set here. I call it A. Okay, how small it has to be, let me also defer this. And I start to hit this A with G. So this will be G of A, G squared of A. I'm not claiming that all of these are disjoint. I actually start with an arbitrary small, very small set. It might vary. Just for the picture, it's convenient to draw all of these to be disjoint. And I draw m of them, like m concept, like up to t to the actually m plus 1 consecutive parts of that. Now I want this whole thing to be small, so I'm going to choose A to be arbitrarily, to be small enough in order to guarantee that this whole thing is small. Now there's a delicate point here, that you should always be careful. We are not in the measure preserving situation. So you can say, okay, you pick your A, no matter how small you pick it. What is your control over, maybe it inflates too much and, you can't avoid this set being big. The point is that it's kind of a basic lemma in Radon-Nikodym derivatives. We are assuming that our action is non-singular. So it's kind of a lemma, a standard lemma, that for every epsilon there is a continuity of every non-singular map in the following sense, that for every epsilon bigger than 0 there is some delta bigger than 0, such that if mu of A is less than delta, then mu of G of A is less than epsilon. Continuity in this sense of the word. Of course, this delta does depend on G, but it does not depend on A. So, and this is, it's not a difficult lemma. In fact, I didn't know it. It was kind of an obstruction for us for some time until I realized that this is. But this is not a difficult lemma. It's just some fact about Radon-Nikodym derivatives. And if you hit it with this, you see that if you choose A small enough now, you can make sure that this whole set, which I call B, just the union, I goes from 0 to big M of G to the IA, is such that mu of B is less than epsilon over 10, or not just even u of B, sorry, mu of B union with G inverse of B is less than epsilon over 3, let's say, okay? So not only this set is small, but even its translate is small. Sorry, what did I say here? I apologize, this is not my construction. Here I use G, but here I use T. Okay, so to emphasize it, let me draw it more regularly, okay? Here is my set A. You believe me, it's small, but I draw it just a little bit bigger for visibility. And here is like T of A, T square of A, all the way up to T to the M of A. This is my set B, and also I want, so B is this union. I goes from 0 to M of T to the I of A. And also I want its, this B, and also its inverse image by G to be small, to have a very small measure. And now I'm going to vary G again by just replacing it by the first return map. Where? Into the complement of this little set B. So this B is very small, and I want to leave all. I want it to be. I want it to be very close to B. So as long as I'm outside, I'll just keep acting the same way that I did. But once I enter somehow, then you see the structure. I'm kind of bound to, at least by T, to stay inside for a long time. And this will somehow give me this kind of zebra structure. So, by the way, how much time do I have? 5 minutes? Okay,
We started a bit later.
What?
No, we started a bit later, so.
So this construct, so replace G by H, which is the first return map, to the complement of B, and this will render the following zebra structure. On each orbit, as I drew it before. Let's convince ourselves. Okay, so these black stripes now are exactly the periods where I do enter the group B, and the white stripes are the points where I do not, when I'm outside of my set B. And you see, these will typically be smaller because the whole set B is small. So now, as long as I'm outside, well, no matter what A just acts, this is A, okay, no matter what A just acts by translation, and B acts by this kind of limited range finite permutations, and if I get close to one of the black zebra stripes, well, once I walk in, B starts doing nothing. Okay, it might, the first step might actually hop in pretty far, but not more than M steps away from where I was. And here, this is M steps deep. So there's no way that B is going to traverse any one of these black stripes. Its orbit eventually has to come back. Okay, it has to come back, and deeper into this thing, it will actually start acting trivially. And the same. So the B orbits are kind of limited. They're limited from both sides. Okay, they are kind of separated into this. So here's the thing I'm most proud about in this paper. It's not a mathematical thing, it's just a linguistic. And it's not even mine, it's my co-authors, but I like it somehow. So what happens if you're not doing F2 but F27? Well, then you have 1A, but 26 B's to take care of, B1 up to B26. And you want all of them to actually share the same zebra structure. So how do you call a collection of 26 different group elements that share the same zebra structure? We call it a dazzle of zebras. A dazzle of zebras. Right, it's a kind of a, if you're into names of families of animals, that's how you call a big group of zebras. Because, but anyhow, that's just a side remark. Let's finish the proof, and I'm finishing the proof now by taking M to be even much bigger. Okay, so now take M to be even much bigger, and note that now I'm not acting with B anymore, but what I'm interested in is this word omega that I fixed in the beginning of the proof, and I want to see how this omega acts when I'm acting so this might be like t to the 17, b to the minus 5, t to the minus 3, and so on. Some complicated but predetermined word in T and H. And let C be phi A, or not phi no, eta A of omega, where eta is the homomorphism that just, counts the occurrences of A. So if eta is 0, if C is 0, this means that A is a balanced word here in this group, that I have as many positive as negative powers of T counting with the exponents, and it can be anything. Without loss of generality, I can always assume it's positive just for the picture, no negative just for the picture. And this really is the way in which this depends on the word. Somehow this will determine the dynamics, or depending on the word will really depend on this point C. Because let's see what happens now, okay? I'm starting to walk with my word here. I'm applying, I have absolutely no control over what happens. But as long as I'm in a white stripe, I'm between two black stripes, and I'm just applying my letters. And I'm applying W again and again and again, and at a certain point, at some point in the middle of the letter, of the word, I'm applying it letter by letter. I have no control over. But at some point, I'm going to find myself falling into one of the black zebra stripes. And once I get deep enough into, let me enlarge the zebra stripe now. So here is my zebra stripe. And it emerges from here and from here, and I might come in and then come back out again, I don't care. But once I get deep enough into the black stripe, there is some bound here that depends only on this is some bound that depends only on the word length of omega and the range of h, right? I mean, I have at most some big N letters, and each one of them acts either by translation of one or by translation of at most m. So there is some depth here that I cannot really pass with one instance of the word. Okay, and assume I got into here. Okay, I'm trying to assess the condition of what does it take to pass from one white stripe up to the next one. Okay. Once I got here, well, the action of the group element becomes very, very deterministic. The B elements just don't do anything, and the A elements just move one place to the right. And since I assumed without loss of generality that my C is positive, then once I pass this threshold, this word will just traverse one step of C at every time. So the first time I'm applying the beginning of the word, it will end exactly deterministically C points to the right, and then another application of the word, and so on, until it's bound to emerge from the other side, and then there's no way that it could come back. Okay? So what I get here is a situation in which last sentence. I get a situation where every T orbit contains a bounded number of W orbits to begin with. So this doesn't imply ergodicity, but it does imply a slightly weaker condition that there are at most so many bounded number of infinite ergodic components for the action of this cyclic group generated by W, and this is enough to establish conservativity. Good, thank you.
Time for very, very quick questions. I have a question. So, can you start with some set that you have a uniform upper bound on the time to get into a zebra, a stripe? So you're in a zebra stripe.
Mm-hmm.
You go out and you get in again.
Mm-hmm.
And you go out and you get in. And to have a uniform number of moves, that if you start from a zebra, you get into a zebra, and then you get into a zebra.
Well, somehow, first of all, it depends on the word W, right? If C is 0, so if W is a balanced word in terms of the exponents of T, then it will just not traverse zebra stripes. It will stay within one stripe, maybe, dipping into the black stripe from the right, from the left, but coming out again back, okay? On the other hand, if the exponent is positive, then it's bound to have some infinite orbits, because within the black stripe, you see, you just pick a point here and you start hitting it with W. It will go to the right and come from the left or the other way, depending on the exponent. So what you're basically asking is if you have any control on how wide the white stripes are. Right, so not in this general construction, but if you want to restrict your attention to a nice, like a very good example of, and this was actually our first construction, a very good example of a non-singular system is what you will call a non-singular odometer, which you just think of as, you take, say, the V2 and the regular odometer, but you weigh the zeros and ones in the dyadic integers differently. So in such a way that the weight of zero, the ratio between the rate of 0 and the rate of 1 is P. And this will give, or lambda, not P, and this will give you something of type 3 lambda, a measure of type 3 lambda on the odometer. And there, in that setting, we have nice constructions where you can actually, give very, very regular zebra stripes for that specific thing. And, if you're willing to vary your because all of the 3 lambda things are orbit equivalent. So if you are willing to, if you care just about the orbit equivalence type of your equivalence relation, you might as well choose this as your generator to begin with.
Okay, so time for coffee and more discussion outside.
Yeah, cool. Thanks.